SI 유닛 간단하게 설명 듣고 끝냈는데요. 이 SI 유닛 쓰는 걸 주의하시길 바라고. 네, 그래서 첫 번째 시작을 하겠습니다. 이제 영어로 진행할게요. So the first chapter covers the property of gases. You might wonder why gases are just studied first instead of other states such as liquid or solid. This is because gases are the simplest state with minimal intermolecular interaction, making them fit ideal condition more accurate than other places. So we will begin with the ideal gas law, also known as the perfect gas law, and then extend the concept of the equation of state from the perfect gases to the real gases. And for real gases, we will explore the molecular interaction, the van der Waals equation, and principle of corresponding state. So let's first discuss the properties of gases. As I mentioned, the gas is the simplest state of matter because it has the least intermolecular interaction among phases. So this simplicity allows us to study its properties more easily, and the gas is a collection of molecules in continuous random motion. And also their properties like that. Their average speed increases as the temperature rises, and the distance between the molecules is much greater than the liquid and solid, resulting in the weaker intermolecular forces. So a perfect gas is an idealized model of the gas that follows a specific assumption, making it easier to analyze and predict its behavior under various conditions. Yeah, first let's study the state of gases. State, 한국말로 이제 상이라고 부르는데요. The physical state or simple state refers to the condition of the substance, which is defined by the physical properties. For example, the amount of substance and the volume of it occupies, V, the pressure P, and the temperature So we can describe the state of gases using this equation of state, which expresses the relationship between these four variables. For example, in general form, pressure is a function of temperature, volume, and the amount of substance. This means that if we know like the temperature, volume, and the amount of substance, then we know that the P is a known value. So the first one is determined. And for the perfect gas, the equation of state is given by the ideal gas law, such as P is equal to nRT divided by V. I think you should learn from general chemistry or general physics. And R is the gas constant. But we will explore this equation details soon. Before that, let's begin studying the variables one by one. The first variable is the pressure. So pressure, as you know, is defined as a force divided by the area over which the force is applied. So mathematically, it is expressed as P is equal to force divided by area like this, where the P is the pressure, F is the force, and the A is the area. The SI unit is actually Pascal, which is equal to 1 Newton per square meter. But when you're reporting or when you read the paper, you will see bar more than the Pascal, which is the standard pressure used for reporting data is 1 bar, which is equal to the 10 to the power of 5 Pascal. Yeah, I don't know why, but bar is more common unit than the Pascal actually. Although this Pascal is the official SI unit, other common used pressure unit include the bar, this atmospheric pressure at sea level, which is ATM, and pound per square inch psi. If you will work in the field, you will see this psi a lot when you are dealing with gas. And from the perspective of gases, pressure originates from the continuous collision of gas molecule is with the wall of their container. So this collision exerts force over an area, resulting in pressure. And if you look this schematic, if two gases are in the separate container that shares a movable wall, the gas with high pressure will compress the gas with the low pressure, like in this direction. As the high pressure gas expands, its pressure decreases, and while this low pressure gas is compressed, causing its pressure to increase. So eventually the pressure will equalize and the wall stop moving, reaching a state of mechanical equilibrium state. So this mechanical equilibrium occurs when the pressure is equal on the both sides of a movable wall, and the pressure. So the pressure of the gas indicates whether its container will be equilibrium with another gas in the shared system, something like this. For example, the famous mercury barometer is used to measure the atmospheric pressure. In this case, the movable is mercury itself, which is displaced by the pressure exerted by the atmosphere. So the height of the mercury column is directly proportional to the external pressure, which is the 1 atm in here. So 1 atm is 764 millimeters of mercury. This is the height of this mercury column. So they are in a mechanical equilibrium. Another important variable is the temperature. So the temperature is the temperature determines the direction of energy flow as a heat when two samples are placed in contact through the thermally conducting wall, which is a diathermic wall. This process is quite similar to mechanical equilibrium in pressure, but instead of pressure equalizing, the energy or the heat flows. So this wall will allow the thermal energy to pass through, and as shown in this figure, heat flows from the sample with a high temperature to the one with low temperature until the equilibrium is reached. So in this case, like from the high temperature, energy flows to the lower temperature, and the lower temperature system will increase the temperature, then the system becomes equilibrium. We are generally familiar with the Celsius scale. I think, for example, today is 10 degrees Celsius, something like that. But since it is based on the boiling point of water, it may not be suitable for our materials. So instead, we use a more precise thermodynamic temperature scale measured in Kelvin. So then the relationship between the thermodynamic temperature Kelvin and the Celsius temperature is given by this equation, which is T is equal to theta plus 273.15. So where is the T is Kelvin and theta is the temperature in Celsius. Yeah, so this is about the pressure and temperature in a scientific definition. Then let's move on to the perfect gas law. So the state of a pure substance is determined by specifying its amount and the volume and the pressure and the temperature. And for the perfect gas law, it is defined by experimentally. So it has been established that specifying any of three of these variables is sufficient, as the fourth variable is then automatically determined. This means that like the equation of state can be written as something like P is a function of temperature, volume, and the amount of substance. And as I mentioned, like if these three of variables are known, we know the last one, like P, which is fixed. And one important example of this equation of state is the perfect gas law. P is equal to nRT divided by V volume, where the R is the gas constant. And this equation was established by combining a series of empirical laws, meaning it is based on the experimental observation rather than the theory. So, like scientists do the many experiments, and they found that there is a relationship between pressure, volume, and temperature and amount of substances. For example, you should familiar with Boyle's law, which is a state that pressure is inversely proportional to the volume when the temperature and the amount of gas constant. And the Charles law states that volume is directly proportional to the temperature when the pressure and the amount of gas are constant. And Avogadro principle states that volume is directly proportional to the number of gas molecules when the pressure and the temperature are constant. So I think these laws are quite intuitive. For example, if temperature increases, gas molecule becomes more active, and they will collide with water more frequently, and the volume is expand to maintain the constant pressure. Or when the temperature rise, they collide more to the water, then the pressure or the force increases, so the pressure increases as well, like this. This is the 3D plot of pressure, volume, and the temperature. So in the graph, the curve corresponding to the same temperature here, which is called isotherm. And the curve corresponding to the single pressure is known as isobar here. And the curve corresponding to the single volume is called isoform. Isotherm and isobar, you will deal with this condition a lot, so I think you should be familiar with this name. Yeah. Finally, this empirical observation can be combined into a single expression, which is a PV constant multiplied by amount of substance and the temperature. What is this constant? This constant of proportionality determines experimentally to be the same for all gases is called R, the molar gas constant, and this leads to the perfect gas law that we already know, and the gas obeys this equation under all conditions is known as the perfect gas. However, for real gases, they more behave like a perfect gas only when the pressure approaches zero. So when the high pressure or the moderate pressure, they don't act like a perfect gas. Exception is only pressure approaches zero, where the intermolecular interaction becomes negligible. And 혹시 질문 중간에 있으면 손 들고 질문하셔도 됩니다. Okay, let's continue the lecture. The perfect gas law is fundamental in physical chemistry because it serves as the basis for deriving many important relationships used throughout thermodynamics. So you will encounter various applications of this perfect gas law in upcoming lectures, so should be familiar with. And for practical use, the molar volume is important, which is a volume divided by the number of moles, can be calculated under specific conditions. For example, here standard ambient temperature and pressure, SATP, defined as the room temperature, 25 degrees Celsius, and the 1 bar. In this case, under this condition, the molar volume of perfect gas is 24.789 liter per mole. And another condition is standard temperature and pressure, which is STP. This defined at 0, 0 degrees Celsius and 1 atm, and the molar volume of a perfect gas is 22.414 liter per mole. I think that you should know this volume around. So remember this one. And the gas constant is determined experimentally under this condition that 1 mole of an ideal gas occupies 22 liter at 1 atm and 0 degrees Celsius, so which is known as STP, like in the previous slide. So under this condition, the value of R is 0.08206 liter atm per Kelvin per mole. And when expressed in SI unit, it becomes the 8.314 joule per Kelvin per mole. I think we will use this number very well, and then which is more commonly used value in the thermodynamic as well. So remember this one as well. And the gases we encounter in real situation are often mixture rather than the single component. Think of the air, which consists of multiple gases such as nitrogen, oxygen, and other things. So when dealing with the gaseous mixture, it is often necessary to determine the contribution of each component to the total pressure of the sample. So the partial pressure of the gas J in a mixture, which is defined like this, Pj is equal to xp, where the P is the total pressure and x is mole fraction. So this mole fraction is given by this equation, which is Nj is the amount of component J, and the N is the total amount of gas molecule in the mixture. So this relation implies that regardless of the mixture's composition, the sum of all mole fraction equals to 1, and the sum of all pressure equals to the total pressure. So this relation is true for the real and the perfect gases, so you can use this equation for any cases. And actually the concept of partial pressure originally was identified is Dalton's law. According to the law, the total pressure exerted by gas mixture is the sum of the pressure that its individual gas would exert if it occupies the container alone. However, in this law, is strictly valid only for the perfect gases. So in general, the definition of partial pressure follows the equation of this law. So this is only for the perfect gases. Okay, now let's explore the kinetic models of gases. So in this chapter, we will derive a powerful quantitative conclusion based on a few simple assumptions about gas behavior. And this kinetic model provides understanding of gas properties by linking the macroscopic observations such as pressure and temperature to the microscopic motion of gas molecules. So for example, like Boyle's law states that PV is equal to the constant and the constant temperature. But from the molecular perspective, if a gas sample is compressed to the half of its volume, the number of molecules striking the container water per unit times double. So this results in increase in force, and thus the pressures are also double. And they follow this equation. And similarly, in Charles' law, it states that volume is proportional to the temperature when the number of moles and pressure remain constant. But from a molecular viewpoint, increasing the temperature raises the average speed of gas molecule, leading to more frequent and forceful collision with the container water. So this causes the pressure to increase, which can expand the volume if the external pressure remains unchanged. So the pressure becomes unchanged, but the volume increases according to the temperature. following this equation. So we can now transition from this qualitative understanding to the quantitative mathematical model known as the kinetic model of gases. Let's drive it. But before that, here are some assumptions for this kinetic model. First, the gas consists of molecules of mass n in ceaseless random motion, obeying the law of classical mechanics. And the second, the size of a molecule is negligible in the sense that their diameter are much smaller than the average distance traveled between the collision. So they are assumed like a point-like. And third, the molecules interact only through the brief elastic collision. So, for example, the total translation kinetic energy of molecule is conserved, which means that the conservation of energy. Yeah. So, with this assumption, it is possible to drive a model that relates to the pressure and volume of gas. This one, and let's do that. I'm gonna use the formula here. The pressure of gas using the kinetic model is PV is equal to 1/3 which means here this one. And if we think the one gas particle, there is a gas molecules, but point-like, very small, and then it travels with the velocity of a Vx along the x-axis, and when they collision with the wall, it is an elastic collision, so they don't lose their momentum or energy, so the velocity does not change. And the linear momentum changes from mvx to minus mvx for one particle. The linear momentum change, you know. Where is the y and z component? It is actually y and z component are not changes since elastic collision with the wall perpendicular to the x-axis. And then we are going to consider this y and z-axis at the end of this model. And if I draw this one in 3D, sorry for bad drawing, but you can check the drawing in the slide. This is the area of A, and so there is a particle, and then in an interval time delta t, this molecule with the Vx can travel a distance length. They can travel this line with the distance Vx multiply the delta t over the x-axis, and all molecules in here in this volume will strike wall here. So these all molecules will travel this volume and then hit the wall, which makes the collision and the pressure. Then we can say that if there is n molecules, the particle density in this volume, we can say that so n is the mole, and the this Na is the Avogadro number. So this means the actual number of particles. So more is just the indication of one more, two more, something like that, and Na is like the actual particle number. So if you multiply this one, and we can get the number of particles in this volume, and then V is means that this volume here. So we know the distance here, or L. We know the area. Then this becomes the So this is the volume V, and then we can calculate the number of molecules with using this particle density. So the particle density is Na V, and we know the V here, V x like delta times T, and A the area. So this particle number, I mean the number of particles links to the collision number, because this particle, every particle will hit the wall, makes a collision, and makes the pressure. And another thing we should consider, you remember the assumption number one, it says that it's the particle is the in ceaseless random motion, meaning that even if particle is here, we don't know where it goes, like which direction they will go, we don't know that. So we can assume that half of them goes to the left and the half of them goes to the right, but the half will not collide with the wall, but only the half one will collide with the wall. So the average number of collision becomes hard, and this becomes something like this one. And now we know that the average number of collision or average number of particles that collide toward the wall, and then we can calculate the total momentum change by multiplying this average number of collision and momentum change over one particle. So let's write this equation like this. Then it becomes the okay. For sequestration is N and Na is N, which is the gas molecule weight per mole, and we can simplify this equation as well. And from the Newton's second law, which is the P is so the momentum change is force multiplied the delta T, something like this one. And then we know that then F becomes So force is the momentum, linear momentum change divided by the interval delta t. So it becomes, so we are gonna use this one, and then this t will cancel, and the equation becomes then we know the pressure mathematical form, F divided by A. Finally, we can get the pressure of the things with sequence. Yeah. So now we know the pressure along the x-axis only. Then where is the y-axis or the x-axis, something like that. But before that, the velocity of all molecules are not the same. So we're gonna use the velocity to the up with the average velocity, so it becomes this kind of just something like that, and then PV equals something like this one. So we now know that the relationship of pressure and the volume in the perspective of x-axis, and then let's do the y-axis and z-axis. So from the definition of root mean square, this is something like that, and the average values of Vx, Vy, Vz are the same. So it becomes Vx squared all the same in this model, then we can say that like this, and then it's all the same, so it becomes a Vx as well. And finally, Vx becomes the third VRM as scalar. And we will just put this Vx, the relationship between the Vx, VRMS, and the PV and then Vx scalar. So it becomes now PV and so we can now derive the PV relationship from this kinetic motion. I hope you understand this one. It's quite complicated, but if you follow this step by step, you will understand how to derive this relationship. So we can say that if this velocity, which means there depends on the temperature. If we RMS depends on the temperature, this PV becomes a constant, which is Boyle's law. And we know that the perfect gas law as well, like the PV and RT, then you know this, it becomes the same as these things, and we calculate calculate the average velocity of this gas molecule with the temperature and the molecular weight. So if you see this relationship, sorry, here, if you see this relationship, this means that the higher temperature and the higher the speed of gas molecule is easily understand. And if as a given temperature, heavy molecules are slower than the light molecule as well. You can understand like heavier is slower. Do you have any question for this kinetic model? 아마 1학년 때 공부를 하시지 않았을까 싶은데요. 그죠? 모르시는 거 있으면 물어보시면 될 것 같고. Yeah. Now let's move on. Real gases. So how do they differ from ideal gas? Real gas deviates from ideal gas behavior because the molecules interact with each other. So this deviation becomes significant at high pressure and low temperature, where the molecules are close together and the intermolecular forces become strong. And there are two types of intermolecular forces. The first one is the repulsive, which contributes to expansion. This is a short-range interaction acting over distances comparable to the molecular diameter, and it becomes significant under high pressure or low temperature when the molecules are packed close together. And the second is attractive force, which contributes to compression. This is a relatively long-range interaction acting over several molecular diameter, and it becomes less effective when molecules are far apart. And let's examine behavior of real gas while it is compressed from point A to the point F in this pressure volume graph. At point A, the gas follows the Boyle's law. Since the temperature and the pressure are low, meaning the gas behaves like a perfect gas. But as compression continues to be deviates from Boyle's law begin to appear due to the increasing intermolecular interaction because they're close together and the attractive or repulsive force become dominant. At the point C, when the pressure reaches 60 atm, the gas no longer behaves as the ideal gas. Instead, it follows the CDE path, where the liquefaction begins due to high pressure. So in this region, gas and the liquid phase coexist in equilibrium, forming a horizontal segment on the graph. And the pressure along this CD segment is known as the vapor pressure at this temperature. The vapor pressure is defined as the pressure exerted by the vapor in equilibrium with its liquid or solid phase. And as the pressure increases, more liquid forms, and finally at the point E, the gas is completely converted to the liquid. Beyond this point, like point F, further compression requires a sharp rise in pressure, as indicated by this steep increase from E to F. This is because liquids are nearly incompressible, meaning additional compression requires a significant pressure increase. So if we visualize this CD path, we can see how liquefaction occurs during compression. At the point A, liquefaction begins, so meaning some gases start converting into liquid, and as compression continues from A to B, more gas gradually condensed into the liquid while maintaining this constant pressure. And at the point C, the gas is completely converted into liquid, and beyond the point C, further compression leads to only a small decrease in volume. despite this significant increase in pressure. This happens because the liquids are highly incompressible, meaning their volume does not significantly change under the pressure. Yeah, so as we study, the real gases are affected by the pressure. So at the low pressure, molecules are far apart, and the intermolecular forces have little to no effect for most of the time. As a result, the gas feels almost like a perfect gas. At the moderate pressure, attractive force dominates the repulsive force, causing the gas to be more compressible than a perfect gas. This is the molecules are drawn together, reducing the volume more than expected under the ideal condition. And at the higher pressure, repulsive force becomes dominant as molecules are forced very close to each other. Since the repulsion prevents further compression, the gas becomes less compressible than the perfect gases. Okay. And 네, 오늘은 그러면 여기까지 하는 걸로 하고요. 다음 시간부터는 이제 어떻게 리얼 가스를 표현할 수 있는지에 대해서 배우게 될 겁니다. 오늘 중요한 건 이제 perfect 가스랑 리얼 가스를 조금씩 해보고 해서 perfect 가스를 어떻게 표현해야 되는지에 대해서